welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests that have backgrounds in chemistry, biochemistry, and machine learning. And our guest today is Max Welling, who many in the machine learning world know. He has worked on many very interesting papers and projects in the past. Some of them, like one theme of his research has been variational autoencoders. He's also worked on invertible flows, equivariant networks, physics-informed networks very recently. Max, I was very excited to have you on the podcast. Welcome to Machines and Molecules.
Thank you, Ingmar. I'm very happy to be here.
How are you doing today?
It's great. Yeah, today is a good day. We have had like almost a month of non-interrupted rain, and today we have like sun. So I see you have snow in the background.
That's true. Yes, I didn't know it existed anymore. I'm happy that my child will still see snow in his life. So yeah,
Very good.
So Max, you have recently been at Microsoft Research, also at University of Amsterdam. After you've also spent quite some time in your career in Canada. Now, maybe can you tell us a bit about what has motivated you overall in your work and how you think about universities versus industry?
Yeah, good question. So I started in physics, actually in high energy physics, and that was intellectually super exciting and interesting, but it didn't make a big impact because I was working on quantum gravity in 2 dimensions, and so it basically boiled down to writing papers that disappeared in journals and no actual practical impact. So I then decided to do something that's more practical, and I ended up in machine learning. And clearly, machine learning, since I joined in '98, it has really exploded and have had massive impact, actually. I would say that my sort of research has always been guided by this physics background. So I've always tried to remain inspired by all the things I've learned in physics. I think there's wonderful intellectual contributions in physics that keep influencing machine learning. And sort of that sort of journey has continued until today. And more recently, sort of this flow has also been reversed a bit. So these days, machine learning is also influencing back physics and chemistry, and I've been very fascinated by that.
Yeah, this is actually also a theme of your later research, like recent research, right? You've worked on some of this influencing of physics, chemistry with machine learning.
Yes. So that was actually to go back to your question about the difference between academia and industry. So so the good thing about academia is that you can set your own research agenda. You have a lot of freedom, and you can work with young talent. And then in a company, of course, you can have more sort of power to actually build things, and there's more resources available there. So that's an advantage of a company. And so indeed, when I joined Microsoft 2 years ago, that was an AI for Science initiative, where AI was going to help the sort of many interesting application areas in physics and chemistry.
So actually, for context, your PhD, where you wrote these papers that had no impact in your perception, you did this with a Nobel Prize laureate, right? Gerard et Hooft.
Right.
So still you say no impact. Did you foresee back at the time that machine learning would have more impact, or was it just that it was quite practical in your mind and it was not foreseeable at that time that it would basically go through the roof in adoption, really?
Well, certainly I didn't predict, the absolute crazy level that it's gone through over those years, but I was certainly very excited about the possible impact it could have. So I certainly saw the sort of the potential of machine learning for impact. And I was thinking, for instance, about medical imaging and these kinds of things more. Also, later when I worked with Geoff Hinton, so he was super excited about all of this, right? And so he was very infectious in sort of this idea that machine learning was going to change the world. He already saw back then that this was going to happen, and so this also influenced me, of course, a lot.
Would you say this infectiousness is one of the main tasks of an advisor?
Actually, it's a very interesting question. There's many different ways you can advise students. I think perhaps one of the most important ones is to give a good example, to lead by example, and encourage students to pursue their own ideas. And I think if you do it right, you help them when things are not going so well, but you let them go when things are going very well, and you let them develop their own ideas, and you're always there on the sidelines to encourage them and maybe nudge them and steer them. But it's also very important that a student, a PhD student in particular, when they write a thesis, it's their thesis, it's their product, right? It's their foundation on which they build their career, and so that it is a bit of a sort of subtle act, I think.
Both of your advisors, Geoff Hinton as a postdoc advisor and Ed Hooft as a PhD supervisor, they were extremely successful in their fields. You are also a very successful academic offspring. What would you say did you apply, or what would you apply in hindsight? What would you like to apply of what they did well in hindsight? Sometimes.
I have a very clear answer to that, in fact, because what both of them did very well is that they basically worked from their intuition. So both of them somehow they could do math well, but they somehow disliked it in some sense. They would say things like, I'm not good at math, or I don't want to apply all that math. Or I remember when going to Hooft, I would write math on the board, and he says, like, and he would wipe it all out, and then he would say something like, let's imagine you have an orange and you cut out a piece of an orange, right? So this is the way they think. And for Geoff Hinton, exactly the same, right? He would be incredibly intuitive about things. And so that's, I think, the really successful scientists, they start from the intuition. They feel their way through the problem. They know where they want to go. It's almost a religious belief that they want to do this, and they know the answer is going to be there. And then they work their way back, using math or other ways, or coding or whatever, to prove that particular point. I don't personally believe very much. There's some people who can do that. I'm surely not one of them. Where you just start with an axiom, and then you start sort of, okay, what are all the implications of this particular axiom, and report on the good ones. I think it's much more the opposite. You go like, I believe the world works like this. How do I get from here to there? How do I find proof? How do I build a case for that? And I think both Geoff Hinton and Gerard at Hooft were incredibly intuitive scientists.
That's interesting. Okay. And did they do something special so that, maybe not special, but what would you say helped to not be intimidated by the success of these people? Because we see this again and again, like people that are very successful, but they don't manage to teach other people to do the same.
Yeah, it's hard to say a little, because I don't think either of them was a particularly good teacher. So it's not like they excelled in explaining their ideas to others. I think in some sense, both of them live on a somewhat different level even. It's the task of the student to try to translate what they say, right? To try to understand what they say, and then work from there. And if you can do that well, you can work well with these people. Also, you have to be quite independent, I would argue, and not rely too much on too much guidance. But I think the goal is to try to get to the same wavelengths as they are, right? To try to understand, to get in resonance with the way they think. And once you get to that, you can get very excited about something together. And then, you try to help this person with reaching that particular vision or sort of materializing that particular vision. And of course, they're very excited about that, right? If you have a vision and there's a student who believes you and is working with you to sort of to achieve that, then they get very excited about it. And then you have a real collaboration.
That's very interesting. So you told me before we started recording that you have both left Microsoft Research and you're not like really full-time in university. Why is that? What are you looking to do? Why did you decide to go out of these two endeavors? And what are you looking to do next?
Yeah. I should say I had a very good time at Microsoft. I left not because I was necessarily, disgruntled about anything at all. So I did notice that I personally I find it very important to stay very connected to the technology and the content. And sometimes you get promoted into places where you don't have that. And so I realized I really need to work with students, and I need to work with I need to stay with the technology myself. And so that was the reason I decided to leave Microsoft, even though I think the initiative, certainly AI for Science initiative, is really a fantastic initiative. So I also decided, so my wife basically told me, Max, don't make a decision for your next thing for 6 months because you'll regret it. Let's do a couple of good things. We went on a month vacation to Italy. Now I'm graduating students and I visited CERN. Then I go to NeurIPS in New Orleans, and then I have 2 months at Caltech on a Merkin fellowship. I will do research there. And then after that, I probably make a final decision what to do next. But I do know that whatever it's going to be, there's two things which I find important. First, I want to stay with my feet in the mud in terms of technology. I like to collaborate with people, so that's good. And I want to make an impact, a positive impact in the world, using that technology that we developed. So, for instance, the thing that I find most important is climate change, and see if we can use machine learning to help mitigate some of the challenges around climate change.
Yes.
And I'm looking at big tech, but I'm also looking at startups, for instance, or even academia. I have whatever it's going to be, it's undecided at this point.
Yeah, I understand. Yeah, this is very interesting. Actually, a few years back, I think, among others, Andrew organized a workshop at NeurIPS about climate change applications of machine learning. And back at the time, I was like, yeah, that would be really nice, but how? How can we use classifying images into cats and dogs for this? Back at the time, I think it was very unclear. Now, with the company that we've formed, that's kind of one of the major motivations. And I think chemistry and physics really is one of the keys, right?
Yeah, absolutely. There's a whole new field. Actually, that's the thing I'm most excited about in terms of technology. But there's a whole new field emerging. That is how to use machine learning to advance the sciences, right? And this goes from improving calculations in quantum chemistry, like DFT calculations, to accelerating molecular dynamics using force fields, all the way up to sort of accelerating this, for instance, weather prediction, like Navier-Stokes equation, using sort of what we call neural surrogates for these sort of numerical integration methods.
Yes. Yeah, definitely. I mean, it was very clear that machine learning progressed quite easily in image classification, language models, and so on and so forth, because there was so much data available and it was so easy to progress there. But it's also very exciting to be able to influence the real world, like the physical world around us. To me, this was like one of the big things. I was
Yeah.
always like keeping away from chemistry for some reason, even in my postdoc where everybody was doing machine learning for chemistry. But it is quite fascinating that you can do this, that in essence nature behaves in very simple, statistically speaking, simple ways.
Yeah, I wonder if it's simple though. So I think so. First of all, molecules when they evolve is like a highly chaotic motion,
Absolutely, yes.
and it happens at all scales. It's like also an Navier-Stokes equation. You know, when it gets chaotic, it's basically across many scales, and all these scales interact with each other. In
Yeah.
quantum mechanics, clearly, exponentially difficult to simulate classically. So I don't think of nature as simple. I mean, there's certainly structure that can be captured by machine
Yeah.
learning, but not all structure. Um, but yeah, it's fascinating. You can make progress at all in some sense, and in some
Yes.
way, you can think that nature is the best computer of all, right? I mean, nature is a big computer. It's just very hard to program. It's very hard to control. I mean, an
Yes.
experiment would be controlling nature as a computer, and that's why Feynman at some point also said, we should build a quantum computer because that's sort of
Mhm.
quantum mechanics, controlled by humans in some sense. So yeah.
Yeah. Yeah. I mean, you're right. If we want to understand each and every part of nature and be able to simulate, for example, molecular dynamics only faster, then things can get very complicated and messy. But there are some applications of rather basic machine learning where you can make a strong impact, and people just have never heard of this. Simple things such as, I don't know, you're trying to find the best molecule to do X, Y, Z. And the models that you can also use for that are simply string representations with all the downsides of this, of a string representation for molecules. But it actually works, and it works pretty well
Hmm.
oftentimes. So
Yeah.
this has been fascinating to me.
It's surprising, isn't it, that these
Yeah,
techniques, they're quite general techniques, like language
yeah,
models or sequence models can find this complicated structure somehow. I mean, this is of course where deep learning really excels, right? It's like
yeah,
finding this hidden, really complicated structure. But
yeah.
it's fascinating. There is all that structure, and it can be discovered by machine learning. Yeah.
Yes, absolutely. You've speaking of deep learning, you've worked, I think, in many different um, areas of or technologies of machine learning, deep learning, one of them, but also you've done a lot of Bayesian work, and I think you worked with kernels. What is your general view of the current trends?
Yeah. Yeah. It's a good question. So the thing I liked most was graphical models somehow, because
Mhm,
graphical models was intellectually very stimulating, and the reason was that you were actually modeling. You were really thinking
mhm,
about, okay, what is the structure of the world and how do I impose it on a model, and then how I do inference in that model. And in fact, these calculations were very aligned with thermodynamics and statistical
mhm.
mechanics. You write down the free energy and you do relax the free energy over variational distribution and all that. Um, so these days, but undeniably, deep learning is has had much more impact and
Yeah.
is a much better predictor
Mhm,
than these graphical models. And so the new paradigm is, if you have a lot of data and a lot of compute, somehow these deep neural networks, they put the right prior on things in
mhm.
such a way that they become incredibly predictive and not even start overfitting. So there's this whole new field of,
Mhm.
if you make these models almost with an infinite number of parameters, they start to reduce overfitting. And that's something that's really not well understood at this moment.
Yeah.
I should also say that, and that's probably me getting old, that the fact that it's become more and more software engineering now, right? So some of the
Yeah.
models, like the OpenAI models, instead of getting more complex, they become simpler simply because you can scale them to bigger systems.
Yeah.
And software engineering is not something I was educated for, and I don't find particularly exciting, except for that I understand it's very necessary. But it's the field. So one part of the field, in some sense, is evolving in this scaling is all you need direction,
Mhm.
which is the direction that works, and is also the direction that I find least interesting, which is sort of a conundrum for me because I like to be on the other side, which is where all the intellectual challenge is, and the richness of the intellectual challenge on the sort of scientific side and the modeling side. But that's the part that doesn't perform as well as the scaling part. So that's an interesting tension there. And so I kind of, yeah, I sort of try to make sure I do a bit of both to make sure I don't ignore this important fact that the scaling is the part that's really work. At the same time, also try to go to places where there's still a lot of green grass in terms of modeling.
Yeah. Yes. It's interesting you say that. I also had the impression that maybe one of the strong points really of the deep learning approach is that you can tinker so much. So it's a lot of heuristics that you can apply, and some of it will just work. Interestingly, that's also how when children learn and you just let them tinker, they often learn pretty quickly. So it's probably a good paradigm to be using. Um, your intuition, basically, in reference to what you said about Geoff Hinton. Mm. And yes, I also found it quite interesting that OpenAI really used a lot of good engineering to get these models perform so well.
But that's basically what they did, right? I mean, it's like there's
Yeah.
some smart things they did with human feedback and stuff like that. But
Mhm.
the real advance was to use Microsoft's massive cloud infrastructure to scale these
Mhm.
models and have the vision that that's going to make the difference, right? I mean, not every, I
Yeah.
mean, it's a big bet, right? You're spending $1 billion on this bet, and you sort of have to be sure that it will pay off. And so OpenAI made that bet, and it paid off for them, and it's that's to their credit.
Yeah. Yes, I think that's true. There's always the danger for me to sneer at this, but at the same time, like it's really astounding what you are able to do with this.
Yeah, there's something super interesting about this. In fact, this many people say it's a statistical parrot, right? It's like the way it
Mm,
was trained is so simple, but it's like you
mm,
try to finish sentences or mask words in a sentence and then try to predict it. It's just
mm,
a statistical parrot. It can't be intelligent. But I don't buy into this. So this model is extremely complex, and out of complexity emerges things that are more than the microscopic things.
yeah.
And you see this in physics as well, right? So if you go from molecules to Navier-Stokes, you get a lot of new richness that's happening, new physics that's emerging out of
Mm,
that coarse graining. And I think that's what we are witnessing here. We are witnessing the emergence of certain kinds of intelligence out of complexity.
yeah.
And that's perhaps a whole new interesting field of how to study that, right? How do we study that process? And I'm sure there's a lot to follow on that.
Yes, the type of machine learning papers that are published has also like there's a new type that has emerged, like prompt engineering at NeurIPS and ICML, which is something I think we would never have seen 7 years ago or something.
Exactly. Whole new jobs. Yeah.
Yes, yeah, definitely. Um, so maybe to switch gears a bit, the theme of our podcast is machines, molecules, and a third M word. Have you brought a third M word?
I've brought two, and you can choose. So the first one is Mach, which is, or I'm not sure how you say this in English, but it's basically the speed at which an aircraft, or Mach 1 is when they sort of surpass
Hmm.
the speed of sound.
Hmm.
I always wanted to be a pilot, and
Hmm.
preferably a fighter pilot when I was young. I failed terribly at that in the sense that I didn't get through all these sort of exams, and I was very disappointed about that. And I became a scientist sort of as a second choice. So that was kind of my youth was very much around airplanes somehow, right? I loved airplanes. The other one is magic, and I think there is a lot of. I'm kind of attracted to mystery and magic in some sense. Not only do I like science fiction a lot because there's a lot of interesting, ideas and fantasy. It's even in science where I think I get attracted to things like this. For instance, this idea of emerging intelligence is magic in some sense.
Mm.
Um, but also quantum mechanics attracts me a lot because quantum mechanics is a set of tools with which you can compute things. But I don't think anybody really understands how to interpret quantum mechanics. So how does it really, there's always paradoxes that appear. If you think you understand it, then somebody else comes up with an example, and then again, it looks pretty crazy. And people have come up with absolutely crazy interpretations, like the universe splitting with everything, with every decision that can be made, every every time you can have two possibilities, the universe
Mm.
splits into two, and you get a massive superposition of universes, and you're sitting in one of them. Or
Mm.
things like, whenever a photon from a very distant star hits your eye, the wave function of that entire sphere of possibilities at light years collapses into your eye. I mean, these are pretty crazy interpretations, and I think that's also a kind of magic that I'm very attracted to. How do you interpret that?
Yes, these are two very different M words.
Hmm. That's
And
right.
since we have talked so much about science, I would love to dig a bit into the pilot dream. Um, Also, you're wearing this nice headset, which fits the theme very well. So, how was that? I imagine, like, how did you feel after it didn't work?
Well, terribly, because my entire youth was sort of working towards that. I remember coming back and I kicked my closet and I kicked an actual hole in my closet at that
Wow.
point. I was kind of frustrated, but it also shapes you, informs you, right? Because going
Yeah.
through a big disappointment like that, and getting over that sort of has an
Yeah.
impact on your personality, and I think in the end a positive impact because
Mhm.
you can handle disappointments and you can persevere despite disappointments, and also the lesson that you don't always get what you want, right? It's just a good lesson to have. The world doesn't always cooperate with you. That's fine. You just go to the next
Mm.
opportunity, and there's plenty opportunities out there for you to pick. So I think that's
That's.
certainly, yeah. You also mentioned something else which is interesting, is dreaming. So I think I'm a
Mhm.
dreamer,
Mhm.
and certainly this whole idea of being a fighter pilot was sort of a dream. I've been a lot in my head and imagining being a fighter pilot
Mhm.
and flying or something like that. And so yeah, so I would say dream. I still dream. I think I still
Mhm.
imagine things and dream things, but that's also interestingly I feel good for being a scientist
Mhm.
because I think you need to dream of achieving something or understanding something bigger than you. Um, Also, maybe coming back to your the influence of your supervisors.
Yeah.
So Geoff Hinton, he had a dream like that, right? So his dream was, I want to understand how the brain works.
Yeah.
And so it wasn't about I want to understand how neural networks works necessarily. It was how I understand how the brain works. And there's this story which is true. Every week he would come into my office and he would say, "Max, now I know how the brain works." And I said, "But last week you said the same thing. Can be. There's a high possibility it's not right." Like, no, no, this time I really know how the brain works. And the thing is that I'm pretty sure he understood, the probabilities of things, but it's this drive, this dream that
Mm.
keeps you pushing you forward.
Mm.
I think that's really important that you have to have one of these dreams to think I'm going to figure out this or that, right? And then every week after week you're making progress and you're happy about that progress, but this drives you forward.
Yes, that reminds me of my colleague Harry, who also, like, each and every time we speak again, he says, "Now I understand this model," and then
Mhm.
working on the same model. Now I understand this. So Yeah,
Yes,
it's
but I think it's good. It's a good progress. If you ask him,
yeah.
probably. So, do you really think it's very likely that this time you do understand it because you said it every week? If you
Mm.
really probe him, he would basically say, "Ah, no, sure, I don't think it's really true, but I need this in order
Yeah.
to keep myself going, right?" And sort of, yeah, I think it's a very healthy way to sort of stay engaged and enthusiastic about science.
Yes. So did it also help did it also help going from the fighter pilot dream to a life as a scientist, that in science you can progress rather incrementally? So you
Hmm.
don't have to work towards this one exam on which everything hinges. And then if that doesn't work, you're kind of out.
I think, certainly the dreaming continued in that sense, or this
Mm.
attitude of trying to understand something, the mystery of the universe, right? I mean, it's pretty crazy if you think about, the universe, right? In a sense, like the is like incredibly large, is inconceivably large. It's um, there's so many stars and other objects, and there's so many things we don't know about it. It's like if you start thinking about it, it's also always maddening, right? I mean, where does
Yeah,
it
it
end? Is
is.
every kid asks herself, where does the universe end, right? Is there an end to
Yeah,
it? If not, how can it be that it's infinitely large, right? It's just crazy stuff, and that's the mystery part. And I think it's very good to the way I dreamed about being a pilot and to fly in an airplane just transformed into dreaming about the universe and how does the universe work, and can I understand a little piece of that puzzle, right? And that keeps you going. That's, in fact, being a scientist is one of the biggest privileges, I think, because your life is eternally interesting, right?
it
And
is. That's true.
instead of any other job where at some point you probably have seen it all, this job is like there's an infinite number of interesting questions that you can go after and try to understand. And so I think it's the best job in the world, really.
It is a really great job. Yes. So, on that note about the magic of the universe, thank you, Max, for
Thank
being
you.
a guest in Machines and Molecules. It was really enjoyable talking to you,
Same.
and see you in the next conferences.
Thank you,
Bye.
Ingmar. It was fantastic chatting with you. Thank you very much.
Thank you.